Ever wish you could, like, see inside your own brain? Like, in real time, imagine if we could track brain signals as they're happening. It'd be like having a live feed of our own thoughts.
Wow.
Well, get this, because a new method for analyzing brain activity called ARES might just make that a reality.
Oh, really?
We're diving deep into a paper from the Journal of Neural Engineering all about it, and let me tell you, this research is seriously next level.
Cool. I'm excited to hear more. Studying brain activity can be, well, it's complicated. It's a crazy complex organ.
Yeah, understatement of the year, right? So how does this ARES thing help us understand all that's going on in there?
So traditional methods, they have a tough time dealing with how dynamic the brain is. Like, imagine trying to study a single ripple in a pond, but it's pouring rain.
Oh, I see what you mean.
The rain just keeps changing the water level, right? Makes it almost impossible to isolate that one ripple you want.
It'd be like finding a needle in a haystack that's constantly moving and changing shape.
Exactly. And that is where ARES comes in. It's different because it doesn't need a stable baseline, which is like a perfect unchanging starting point, to pick out those brain signals.
Hold on, back up a sec. Why do we even need a baseline when we're talking about brain activity?
It's all about how we actually measure the activity. See, when a neuron, which is a brain cell, fires, it causes this influx of calcium ions. And we can see that happen because the calcium kind of lights up.
So we're using calcium as a way to see those brain signals, those electrical impulses.
Exactly. Now, traditionally, to understand these signals, scientists compare how bright the signal is to a stable baseline. It helps them figure out how much the signal's changed.
Gotcha. So like if you were looking at a light, you'd compare it to a dimmer background to see how much brighter it got.
You got it. But, and here's the thing, the brain is never really stable, right?
Right.
It's always buzzing with activity. It's what it does.
Yeah.
But that makes it super hard to get a truly reliable baseline measurement.
It's like trying to measure a wave in the ocean while you're bobbing up and down on another wave. Good luck with that.
Huh. Exactly. Plus, calcium imaging itself has some quirks that make it tricky. Like the relationship between the calcium levels and what the neurons are actually doing isn't always a perfect match. And on top of that, that signal can get weaker over time, like those glow sticks that fade.
Okay, so we've got these signals that are hard to see, a noisy environment, and our tools aren't perfect either. Sounds like studying the brain is a real pain.
Well, it's a challenge for sure.
Yeah.
But a challenge that ARES might just be able to solve. Because remember how I said it doesn't need that perfect baseline?
Yeah.
Well, this is where things get really interesting.
Okay, I'm all ears. How does it work around that?
Okay, so picture a heart rate monitor. You see the steady beat, right? ARES is kind of like a detective that ignores that normal beat and zeroes in on any unexpected spikes or dips. Because those weird blips, they're what tell us something really important is happening. They're the deviations from the norm, right?
Right.
Those are what we call residuals. And those residuals, they're often the most telling.
Okay.
They could be a thought, a reaction, you know.
So how does ARES know what's unusual? Like, how does it predict what the brain's going to do?
Well, it uses this really cool statistical method. It's called autoregression. It's kind of like, think about trying to predict the stock market.
Right.
You might look at, like, past trends.
Right.
ARES does something kind of similar. It looks at past brain activity to try to, like, guess what should come next.
But the brain can be pretty unpredictable.
Yeah, you're right. But that's the thing about ARES.
Okay.
It's designed to handle that.
Okay.
It expects that unpredictability. And because of that, it can zero in on those moments that, you know, kind of zig when they should have zagged.
Okay.
And those are the deviations, the residuals. That's where the good stuff is.
So it's like ARES is saying, don't bore me with the normal stuff, brain. Show me what you got.
Yeah, exactly. And because of that, it can pick up on these super subtle brain signals, like the ones that other methods might completely miss. It's like upgrading from this old blurry map to a high-definition satellite image.
Nice. So we're talking high-def brain imaging now. I like it.
Yeah.
This paper mentioned that ARES is better because it has better spatial and temporal resolution. Can you break that down for me?
Okay, so spatial resolution is basically like the sharpness of an image.
Okay.
How clearly can we see those individual neurons and what they're doing?
Okay.
So the better that is, the more detail we get. It's like being able to zoom in on a map and see, like, every single street.
Okay, that makes sense. And what about temporal?
Oh, temporal resolution is like, imagine the refresh rate on, like, one of those fancy gaming monitors.
Oh, okay.
How well can we track these, like, crazy fast brain signals over time?
Right.
So with better temporal resolution, we can see things with incredible precision, like watching a high-speed chase but in slow motion.
Cool. So with Aries, we're getting a sharper picture, and it's faster, and we don't even need that perfect baseline. That's pretty amazing.
Yeah, and the study's findings are really cool, too. Area is able to track these things called calcium waves.
Okay.
And these waves move within the neurons, which is something that's been hard to do.
Wait, hold on. You're saying that we're not just seeing a neuron light up, we're seeing activity traveling inside of a single neuron.
Exactly. It's like we can follow the path of a single message as it, travels through this tiny network.
That's wild.
Imagine being able to actually see the brain thinking, in a whole new dimension.
Wow. So we're seeing the brain think in a whole new dimension. But why should, the average person care about this?
Well, think about it. This research has huge implications.
Yeah.
We're talking about potentially changing how we think about medicine and neuroscience.
Okay.
Imagine being able to, see Alzheimer's in its earliest stages.
Wow.
Way before there are any symptoms.
Yeah.
That's the kind of thing we're talking about here.
That'd be huge.
Early diagnosis is so important for so many of these neurological conditions, but it goes beyond just diagnosis, right? Imagine being able to see how new treatments are working.
Yeah.
At the cellular level.
Right.
That's what's so cool about this.
This paper mentioned brain-computer interfaces, too. Is that something ARIS could help with?
Absolutely. This tech could totally change how we interact with computers.
Okay.
Imagine controlling a prosthetic limb with your mind.
Yeah.
Just like you would your own arm or leg.
Wow.
Or even just communicating directly with a computer just by thinking.
Right.
AREs can pick up on those really subtle signals, so
right.
it could make all that a reality.
That's incredible. But, there's got to be some downsides, right? The paper mentions some limitations.
Well, it's like any new tech. There's always room for improvement. Right now, it takes a lot of processing power to handle all that data.
Okay.
So it's not exactly ready to be used in real time just yet.
So no mind-controlled robots anytime soon?
Not quite yet. But, researchers are always finding ways to make it faster. And imagine what we could do then. It could change how we understand the brain completely.
Yeah.
How we diagnose things.
Right.
How we even interact with the brain. It's exciting stuff.
That's really cool. Well, this has been an amazing deep dive. Thanks for breaking it all down.
Yeah, of course.
And to everyone listening, thanks for joining us for another deep dive. We hope you learned something new and exciting about the incredible world of brain science. Until next time.